Efstratios Manolakis. Efstratios, he got his master and also bachelor in Duisburg in Germany, 2023. Then for some time, almost 1 year, he was visiting in Paris. And nowadays he is PhD in Catania with Rosario Mantegna. His research interests are focused on machine learning-driven information filtering in covariance and correlation matrices. And here we see his presentation. The title is Physics-Informed Singular Value Estimation for Cross-Covariance Cleaning. This is the one I had. The one I can read here is slightly changed. But okay, Efstratios, you can start.
Thanks for the introduction, and sorry that I changed the title. It was a few last-minute changes that I wanted to do.
No problem.
And yes, as already mentioned, my name is Efstratios Manolakis. I'm a PhD student at the University of Catania, specifically in the Dipartimento di Fisica e Astronomia. My supervisors are Professor Rosario Mantegna in Palermo. And then, as was mentioned before this talk, a lot of people went to Paris, and also I went there. And my supervisor there was Cristian Bongiorno. And today I would like to talk to you about my latest research, which connects physics and machine learning methodologies for denoising in financial markets. Can you hear me? Yes, there is no problem?
Yes.
Perfect. Okay, thank you. Yes, so we will, the overview is rather simple. I will give a quick introduction, then the research context and a little bit of the history. Then I will talk about my contribution or our contribution in the field, and ultimately a very short conclusion. So let's start with the introduction. So if you take a look into a physical system and you would like to model it, let's say a system of particles, you would often look at the velocities and position or impulses of those particles. Well, the equivalent in the financial markets would be a system of n assets. So these assets, I will be using only stocks today, but they could be other assets as well. And the main driver behind this, the thing that we would be used to model those, are the returns. So returns is just the percentage change of the price in a given time period. So to measure the interaction between those n assets, a very helpful indicator is the covariance matrix, which, if we would like to know what is the co-movement between an asset I and an asset J, we would just need to do the dot product between the d-mean returns of each of the two assets. So this is very helpful. Another interesting and helpful indicator is the correlation matrix, which you can get if you take the standardized data matrix of the returns. And when I say standardized, I mean to mean 0 and standard deviation 1. And what you can actually do afterwards is the eigenvalue decomposition, which would yield the eigenvector matrix U and the eigenvalue matrix lambda. This eigenvalue matrix is very important because you can do some interesting physics with it, but I will come to this in a moment. And before we continue, I would like to introduce the main problem of my research, or what interests me. And this is namely the problem of noise, or more specifically, one could say it is the statistical uncertainty, which comes up when you have a finite sample size. So this problem has been known for a very long time. So you can see that Stein actually held a lecture in 1975. And when I say a long time, at least for me, okay? So you could think about it in the classical sense that noise would vanish if you held the number of assets n fixed and you would increase the sample size t to infinity. So this would be very nice, but unfortunately we cannot do that because we do not have infinite sample size. On the other hand, what can be done is you can define an aspect ratio Q, which is just the number of assets divided by the length of the samples, the number of samples. Keep this aspect ratio Q fixed, and then move them together to increase them up to infinity. Again, this is a little bit difficult, but you can move this along. So what I would now want to introduce is connected to the eigenvalue matrix, as I mentioned earlier, and the physics you can do on this. More specifically, you could do something called Coulomb-Gas analogy, which was introduced by Dyson in the early 60s. And what this implies is that if you look at eigenvalues, they are actually, they have a similar behavior or pretty much the same behavior as charged particles. So when you hear charged particles as a physicist, you immediately come to the idea of postulating a system Hamiltonian. And this system Hamiltonian is constructed by the Coulomb repulsion, which is, in our case now, the repulsion between two eigenvalues, so they do not want to stay close to each other. And on the other hand, there is a potential V that pushes them again together. So I tried to showcase this a little bit in this picture here. I hope it is clear. But there is one caveat that we need to further mention, is that Dyson, in his first work, he used random matrices. And in random matrices, you can have positive and negative eigenvalues. So a potential like this would be feasible. But in our case, we would like to take a look on eigenvalues of correlation and covariance matrices, which are always, because of the nature of these two matrices, which is they are real, they are symmetric, and they are positive semi-definite, the eigenvalues are always positive. So we have to take care of that as well. So what I would like to do now is to give you a little bit of historical context. So how was noise treated before I came into the picture, let's say. And the first approach was called clipping, so eigenvalue clipping. I would like to draw your attention to the lower plot here. So what we have on the right-hand side, on the x-axis, are the eigenvalues and the probability density on the y-axis. And what you can see is that if you would have uncorrelated time series, the eigenvalue, the probability density of the eigenvalues would converge to the Marchenko-Pastur distribution, pretty exact, to be honest. And then what was done is we took real data, so not me, but people took real 30-minute return data, and they saw that, yes, the Marchenko-Pastur bulk still exists, but there are a lot of eigenvalues that lie outside of it. So even the largest eigenvalue here, you can see that it lies almost at 60, even though the other eigenvalues are most of them lower than 2. This largest eigenvalue has actually also a name, and it's called the market mode. And the idea behind all of this clipping was that, okay, they said uncorrelated time series converge to the bulk. So everything, also in real time series, here in this section of the bulk, is just noise. And people wanted to clip this away and just use the eigenvalues that lie outside. So this is a nice idea, but there is a main problem. And this problem is that you are actually saying or implying that there is no information whatsoever in the bulk. And this is not true. And now what we will do is we will skip a few decades and skip a few ideas, and we will go to something that I also used. And this is called the rotational invariant estimator. So the idea here is to, again, take the correlation matrix, do an eigenvalue decomposition. The reason why it is called rotationally invariant is because U, which is the eigenvector matrix, and you can be imagined as a rotation in space, is not touched. So you do not change the eigenvector matrix U, but what you are doing is you are replacing the eigenvalue matrix with a corrected form. So my research focuses on how exactly can I find this correction function for the eigenvalues. Well, this has a few differences, of course. The first difference is that you are looking at the full spectrum of the eigenvalues, which as a result, you're also including the missing information which was thrown out with a clipping, and you can do nonlinear corrections. So this method is also nice because it has an analytical solution, which is called the oracle solution. And to obtain this, you would need, unfortunately, the population correlation matrix, which I here wrote as C calligraphical. And the main problem here is that even though it is analytically solved, you never have access to the true population correlation matrix because it is unobservable. It has also information from the future, so you cannot calculate it. The fact that this is unobservable, together with non-stationarity, low rank, dominant mode, and a few other problems, is the motivation why we would like to use the physics and a machine learning architecture, which includes a little bit of a prediction. So this is important to mention, into the future. So what we will be doing now is we will try to find this optimal correction without actually having to find this C population. This is the motivation for us to create an end-to-end neural network. So the inputs will be the return time series, so the return tensor in this case. We will feed it through the network. I will talk about it in a moment. And what we will actually have as outputs are the weights of the global minimum variance portfolio. What does global minimum variance mean in this case? It means that if you have a universe of n stocks, you would actually try to find the global minimum of the combination of the variances between those assets that gives you the smallest variance. This is the whole idea. And as you see, the solution is pretty simple because it only needs the inverse covariance matrix. This is also the reason why we can nicely use the rotational invariant estimator. And as mentioned earlier, we will completely decompose it. So the D is the diagonal of the standard deviations. U, this will be adjusted, the D, sorry, I forgot to say this. U, which is the eigenvector matrix, will be left the same as per the rotational invariant estimator. And on the eigenvalue matrix lambda, we will be doing the physics. Because this problem is very specific, we also chose to use a specific loss function. And this choice was also motivated by a few other papers that I did not cite here. But we will actually use the scaled out of sample portfolio variance. So what we will be doing here is we will be training the neural network, and then we will be looking a little bit into the future using this out of sample covariance matrix to calculate the exact portfolio variance. So it has a little bit of a prediction. As I mentioned, this is important. Now I would like to move to the neural network part, which I did not specify exactly. And for us, it was very important to have an explainable neural network, or to know how to interpret it. So what we actually did is, this here is the flow chart, or the schematic representation, and I will walk you through, is we took the inputs, and first of all, we passed them through a lag transformation, because we wanted to understand, okay, how does the neural network like its returns? So how does it look at it? Where is the most information coming from? After the neural network does this part, we split it, as mentioned, into a sample standard deviation, which we pass through a multi-layer perceptron that is estimating the inverse marginal volatilities. And this part is ready. And on the other hand, we calculate the sample correlation matrix on this part. We do the eigen decomposition. The eigenvectors we do not touch because we are using a rotational invariant estimator. Those are also ready. But now we come to the heart of the whole idea, let's say. We take the eigenvalues together with the aspect ratio, which encodes a little bit the dimension. And what we're doing is we are passing them through a long short-term memory kernel. So why is this important? Now we have to remember a little bit the Hamiltonian earlier, which had a repulsion term, so a nearest neighbor interaction, and a global interaction with a potential. So what we saw is that one could imagine, or the mapping is that the nearest neighbor interaction the Coulomb repulsion, can be mapped to the short-term memory of this kernel, while the potential can be mapped to the long-term memory. So it is an exact representation of the system Hamiltonian onto a neural network architecture. So after we did this, we will take the inverse eigenvalues and we can reconstruct the whole inverse covariance matrix, which would yield the weights. So as you can see, by using this architecture, we get the portfolio weights, and as a byproduct, we receive this cleaned covariance matrix, which is what interests me. After we did this, and we've already published a paper on this, the idea was, okay, can we actually generalize this approach, and instead of just looking at square matrices, so the correlation and covariance matrix, can we do the same for rectangular matrices? So now I would like to generalize the main idea of this talk, which is, okay, let's take a look at the system. In this case, let's say a sector of only technology stocks, which has NX assets, and their interaction with, let's say, the healthcare stocks, which have NY assets. The NX and NY is not the same. So the cross-correlation matrix would be defined this way. And as I mentioned, it is not a square anymore, it's rectangular. So we want to see if this also works here. So now I will go into the contribution of this cross-correlation filtering part. So in a little bit more conceptual way, here you can see the cross-correlation part that I mentioned. The diagonal block here corresponds to, let's say, the technology, but it can also correspond to a totally different signal. And the lower part here, the lower block, corresponds to the healthcare. I also wrote this correlation out a little bit differently because we are interested in the upper block, so this CXY, but CXX and CYY will also become very important later. But it is important now to also mention that instead of having an eigenvalue decomposition that we had earlier, we have a singular value decomposition where U correspond to the left singular vectors and V corresponds to the right singular vectors. And our new objective is not to clean the eigenvalues, but the singular values. So this is an emerging field of interest, and we also only found one paper before us, and this actually was used as not only motivation but also inspiration. And this paper was published by Bernard George, Bouchon, and Potters, which is why I called it BBP estimator. And what they did is they used the rotational invariant assumption together with a very lengthy, so about 30 pages of analytical random matrix theory calculation to find an optimal shrinkage. So I will only show this one page, so because it is, as I mentioned, rather lengthy, but I wanted to give you the conclusion of the whole calculation, which is that the cleaned singular values are just the rescaled empirical singular values times, let's say, LZ, which is the oracle function, times or normalized by a resolvent H. So all of the calculations came down to the point of estimating this L and H. So when we looked at all of the this publication here, we saw that our idea will surely be applicable, but there are some points that are still missing. And when I say points that are missing, I mean information that the neural network needs to ingest to be able to do good predictions. So we found out that the information which was missing was the marginal projections, as we call them, which is just the informations of the blocks, but they are transformed in a way that, so they are rotated into the eigenspace of the cross-correlation part. So what we're doing here is we have the upper block, the one that I called earlier the technology block, and it is rotated by using the left singular vector. And we did the same for the healthcare block, but we multiplied it by the right singular vector. So this encodes now some information of the blocks, which is important. What is also important is for the neural network to know the aspect ratio or the dimension of how many assets were in this blocks. And by doing that, we can now define a token for the technology part and one for the healthcare part. So here we will be using, here are the marginal projections, the empirical singular values, and the aspect ratio for this block and for the other block. So there are two blocks, and the fact that there are this two sets of tokens or two sets of information motivated the name two-stream architecture. So this again is a flowchart of our neural network. The first part here is just the information needed for it to work. So again, the gammas here are the marginal information, sigma is the singular values, and Q are the aspect ratios. And what we then did is we looked at the analytical calculations, and for us to estimate the oracle function, we wanted to do this, but now using some code. So we created a shared encoder, which are just some dense layers which we feed through the information. We receive two-dimensional embeddings, which we are summing. And this was enough information for the neural network to again use the physics-inspired neural network from our previous paper. And by passing it through here and taking only the most important singular value corrections, what I mean with most important is because nx and ny are of different shape. Of course, you are only taking the smaller shape in this case. And by having these, you can actually do an additive correction. So what we tried to find here is not a multiplicative correction as the analytical paper, but we tried to find a way of adding this. This will have later also a few other implications, but we will come to them in the last slide of this presentation. And we used the mean square error for all of these for the Azalov's function. So what I also want to mention is that because in the original paper, so in the analytical paper, they tested everything by creating some synthetic data, we also wanted to make sure that our model is not only good in a specific setting, but it also collapses onto the analytical solution. So what we actually did is we recreated the synthetic benchmarks by creating a population correlation matrix C. We did this by drawing a random matrix W, either from a normal distribution or from a symmetrical Pareto distribution with different values. And from this population correlation matrix, we drew some samples and we tried to infer the population. I hope I explained this clearly. So we created the population, we draw samples, and we tried to infer the population. So as I mentioned, we are looking at the mean square error, which means that lower values are better. So the bold-faced numbers here, the neural network, means that it is statistically significant. And I know some of you will look at this plot and see, okay, but here are the same numbers and they are not bold. It is because those are rounded, okay? So in reality, these values are not overlapping, so the significance intervals. But here, even though the numbers are different, they are statistically not differentiable. So what we saw by doing this is that, okay, we have we were able to break down and collapse to the analytical solution. And after knowing that, we wanted to go further to real data. And here is a very packed slide, but I will talk you through it. So here you can see actually the same data, once plotted and once on a table. So the figure actually, for this figure, we set the number of samples to be exactly 500 always. So the sample size is 500. and we varied the number of assets n. So one can see that for the small asset case, the neural network and the analytical case are almost the same. But then as you increase the number of assets, it grows. And it grows rather remarkably in the analytical case, where our neural network stays small. We also found out later, and in the paper it's a little bit more detailed explained in detail, that the reason for that is the market mode. So if you remember in one of the first slides, this enormous eigenvalue that I told you, the market mode, it is so strong that it messes with the analytical solutions of the BBP estimator. So on the other hand, because we did not use a multiplicative correction, but an additive one, we needed to be sure that the resulting matrices are positive semi-definite. And we did this by first whitening the whole correlation matrix, then taking the block, calculating the canonical values, which here you can see on the x-axis. And for the matrix to be positive semi-definite, the values need to be between 1 and 0. So you can see that the analytical method pushes them closer to 0, and our neural network takes this a little bit more to the extreme. I have to be honest with you, I do not know why this second peak actually exists, but we did 32,000 sample simulations, and there were only 4 cases in which this was not the case. Afterwards, and the last thing that I want to show you here is the difference between the two estimations. And this plot actually shows that the analytical method is like a shrinkage. You see it on this gray band here. So it actually shrinks the singular values, while our corrections are a little bit of a more complex nature. And yes, this is everything I wanted to show. And let's come to the conclusions. The key takeaways are that for us, as I mentioned, it was very important to not be a problem-specific, let's say, estimation, but we also wanted to recoup the analytical solutions, which we did. And then we showed more robustness in real data because of the market mode. And our conclusions, or the conclusion that I draw from this, is that if you take an analytical solution, which is most of the time way more elegant, it is very good, but the output and the effect can be even better if you add a little bit of a prediction given a machine learning model to it. So this is what I mean, physics plus machine learning. And some outlooks here would be, for example, something that I'm working right now on, the lead lag dynamics. So if you imagine that you have let's say, realized volatilities, and you would like to know how this evolves with time, you could actually take the data and shift it but by just 1 day and do the same idea. As I mentioned here, 2 types of signals, so the healthcare and the technology sector, but you do it with the same stocks, but just 1 day shifted. So you can take a look at this. And then a way more ambitious direction would be, instead of taking the rotational invariant estimator, you could actually take a hierarchical system, or for example, hierarchical clustering. But this, as I mentioned, is very ambitious, and I would need another PhD for this, or to the time of another PhD for this case. And for that, I'm not actually researching right now on this part. So yes, this was everything. Thank you. And are there questions?
Okay, and thank you very much, Efstratios. Are there questions?
I would like to ask a question. So, sorry, it's very simple, so I don't know the field. So, so you started by an analogy with a Coulomb gas, no? Then
yes,
it's not clear to me if the uncorrelated data correspond to some limit of the Coulomb gas. So the Marcheco-Pastur results from this Coulomb potential, I think, and then.
So I did not understand the question exactly.
The question is,
yes,
do you get Marchenko-Pastur from the Coulomb gas or not?
Yes, but in the case of the Coulomb gas, if you increase T to infinity, you would get the Marchenko-Pastur, yes. Or in this, no, sorry.
If you increase what?
If you increase the sample size, you would get to exactly the, if you increase the sample size, you would get the clean correlation. But actually, you do not know if it collapses to get the Marchenko-Pastur, you need uncorrelated time series. But you do not know if your time series are really uncorrelated. So it does not always collapse to this. Did this answer the question?
Maybe. So not clear to me. So what is this limit of large T? So you are you're taking n finite, and then you take the transversal direction to infinity.
Yes.
And what happens to the Coulomb gas in this limit?
In this, okay. So in this case, you would have the way that we imagine it, which maybe I should have added a further slide, is that the potential of the Coulomb gas. So this potential gets so deep that the empirical eigenvalues fall exactly inside to the specific minima, which means that you have a more exact solution. That is what happens.
Mm-hmm.
Okay, I understand that I did not answer the
no.
question.
I mean, the topic was different of your talk, so you were very, very fast in this part. So,
okay.
Thank you. Maybe we'll look at the papers. Okay, thank you.
Okay. Any other question? Okay. If not, I think we can move to the next speaker because time is running.